hyperconjugation. Hyperconjugation is an effect in organic chemistry, one of those effect in general organic chemistry. So we are starting with the hyperconjugation. Hyperconjugation is also known as no bond resonance. It is also known as sigma pi resonance. So why no bond resonance? No bond resonance because it is actually forming a resonating structure without actually involving a bond. So it is known as a no bond resonance. A resonating structure is formed without actually involving a bond. So how it takes place? This hyperconjugation is seen in actually three types of complexes. Hyperconjugation is seen in carbocation, free radical, and alkenes. We can see some type of hyperconjugation in carbon ion also, but that is negligible. So at first, if we take carbocation, carbocation is something in which the carbon atom contains a positive charge and is also sp2 hybridized. So if we draw the structure like this, so you can say that this carbon is a carbocation. So how will the hyperconjugation takes place? This carbon is sp2 hybridized. If the carbon is sp2 hybridized, carbon is generally sp3 hybridized. But as the carbon is sp2 hybridized over here in carbocation, it has a vacant p orbital. And how are this carbon hydrogen bonds over here arranged? We can draw this. Each overlapping contains 2 electrons. And here there is a vacant p orbital. So we can say that these electrons can get transferred to this deficient electron orbitals as they are vacant. So this causes the hyperconjugation. So how this takes place? If we consider this hydrogen, if this electron gets transferred over here, then we find the structure as this. And the hydrogen goes out as H+. Similarly, if we consider this hydrogen, then the structure comes out as this. And similarly, if we consider this one, then the structure comes out as this. So we are getting three structures where hyperconjugation can take place. So there are 3 hyperconjugating structures. So how to identify how many hyperconjugating structures will be formed in a compound? That is calculated by counting the number of alpha hydrogen. What alpha hydrogen? If we consider this carbocation, this is the carbocation, and the carbon atom attached to the carbocation is known as the alpha carbon, and the hydrogen attached to the alpha carbon are known as the alpha hydrogen. So how many alpha hydrogen is seen over here? There are 3 alpha hydrogen, which denotes that there will be 3 hyperconjugating structures. Similarly, if we consider this structure, here this is the carbocation, these are the alpha carbons, alpha carbon, alpha carbon, and alpha carbon. There are 3 alpha carbon having 3, 3, 3, 9 alpha hydrogen. So the number of alpha hydrogen is 9, which shows that it will be having 9 hyperconjugating structures. So why is hyperconjugating structures important? We should know that more the number of hyperconjugating structures, more will be the stability. So if we consider this structure and this structure, we can easily say that structure 2 is more stable than structure 1, because in structure 2 there is 9 hyperconjugating structure as compared to 1. So this is hyperconjugation in a carbocation. Now if we go back, why is it known as no bond resonance and sigma pi resonance? No bond resonance because here a complex is formed just like a resonating structure. There is shifting of electrons, but here there is no bond. A resonating structure is formed without bond because there is shifting of sigma electron. In resonance there is a shifting of pi electron. Here there is shifting of the sigma electrons. For this is known as no bond resonance. And why is sigma pi resonance? Here we can see there is an interaction between the sigma electrons, that is CH bond, the sigma electrons, and the vacant p orbital. Sigma electron and vacant p orbital. So sigma electron is interacting with the vacant p orbital, and hence it is known as the sigma p resonance. So these are the 2 important questions. Questions might come on number of resonating structures and the stability of the hyperconjugating structures. For free radical, this is a free radical. Here the hyperconjugation leads to the formation of a hydrogen free radical instead of a hydrogen cation. So this is a free radical structure. So here one of the electron comes over here while the other goes to hydrogen, leading to the formation of hydrogen free radical and double bond over here. Similarly, other structures could be so we can see again 3 hydrogen free radicals are formed and 3 hyperconjugating structures are visible, which can also be calculated by seeing the number of alpha hydrogen. We can see that with the free radical, the carbon attached is known as the alpha carbon, and the number of hydrogen present over here is our alpha hydrogen. So here 3 alpha hydrogens are present, which also shows that there will be 3 hyperconjugating structures. Similarly, for alkene, the hyperconjugation takes place by shifting the bond over here, and this bond gets shifted over there. So we get the structure as, and this hydrogen becomes free, forming H plus. Similarly, other structures can be found where this hydrogen is free, and here the third hydrogen is free. So basically we can calculate the number of hyperconjugating structures by just looking at the number of alpha hydrogen. So if we consider this question, what will be the stability order of 1, 2 and 3? So in the first one, this is the double bond complex. If we see, there is no alpha carbon present over here. The hydrogen attached to the alpha carbon are known as alpha hydrogen. These are not alpha hydrogens. So there is 0 alpha hydrogen. If we consider this one, these 2 are the alpha carbons, and this 3 and this 3 are the alpha hydrogens. So we can see there is 6 alpha hydrogen. While in this structure there are 4 alpha carbon actually, containing 3, 3, 3 and 3, 12 alpha hydrogen. And as I said earlier, number of alpha carbon means number of hyperconjugating structure. So there are no hyperconjugating structure in 1, there is 6 alpha hyperconjugating structure in 2, and there is 12 alpha hyperconjugating structure in 3. And I also said that the stability is directly proportional to the number of hyperconjugating structure, which shows that the stability of 3 is more than 2, which is greater than 1.